All right, so we're going to start today by looking at our chapter 11. So format's going to be a little bit different today. I have another engagement to go to kind of toward the end here. So we're gonna go without a break, and we're just gonna cover everything else. And then when we're done, we're with chapter 11. We're gonna call it a day from there. So this is where we were at the end of yesterday. We had talked about Raoult's law and how we can use the idea that different substances are going to evaporate at different rates with different temperatures to separate liquid substances from each other. Now we look at how can that actually impact other kinds of physical characteristics and physical properties. And so what I want you to look at here is the phase diagram for water. And so this area here, which I'm going to draw over, this area here, which I'm drawing over in black, this is the normal phase diagram for pure water. And what we should be able to notice is that if we throw something else into the water, if we create a solution, then what happens is that our phase diagram actually changes to this value right here. So we can see that our solid portion has shrunk and our gas portion has shrunk also. Now, the question in front of you is, why does this occur? Why is it that when we put an solvent and create a solution, why does the liquid region expand for that solution compared to the pure liquid by itself? So why do you suppose that happens? Any thoughts?
Can you repeat the question, Mr. Brooke?
Sure. When we go from a pure liquid like pure water to a solution, let's say, sodium chloride in water, sugar in water, the liquid region in our phase diagram becomes larger. Why?
I'm just going to guess, does it make it harder for the molecules to form like a crystal structure?
Okay, so that in part would explain the expansion this direction, why the solid region becomes smaller. Why does the gas region become smaller?
I'm going to say because the molecule, because it's a dipole-dipole force, so you're going to be adding mass to it as well, so it's going to require more energy to get it to evaporate. That's just my assumption.
You're not far off. It's not about mass. but it does have to do with the fact that it is going to be more difficult to evaporate. Why is it more difficult to evaporate? This kind of goes into what we were talking about yesterday. What exists in this solution that didn't exist in the water by itself? What can we say about the intermolecular forces of this solution compared to those of water?
Stronger.
Yeah. The intermolecular forces in this aqueous solution are stronger than they were in pure water. And so we talked about this yesterday, the idea of Raoult's law, where by increasing the intermolecular forces in that solution, we are able to lower the vapor pressure. And as we saw in chapter 6, a lower vapor pressure will lead to a higher boiling point because the forces are stronger, there are more to overcome, and so it's going to be more difficult to dissociate those forces from each other, especially, if we're looking at something like salt and water. We've got to get the water to dissociate from those ions to go up into the gas phase. And when the forces are a good bit stronger, that means it's going to take more to do it. And on the solid side, we've got that level of attraction that is existing also there. And so what we're going to see is that the liquid phase is going to be far more prominent, and we're going to have a lower freezing point as a result. And we take advantage of this lower freezing point all the time. Anytime that you have to deal with going and doing road salt, the whole purpose of the road salt is to take the water, lower its freezing point, so that's a lot more difficult for the water to form ice crystals. And as a result, a lot more difficult for the road to freeze, or for your driveway to freeze, or for your sidewalk to freeze, or anything like that. So we call these phenomena boiling point elevation, which is a direct result of the decrease in vapor pressure, and we also see freezing point depression here, again, because of those stronger intermolecular forces that exist between the solute and the solvent. And that makes it more difficult for the whole thing to kind of compact and get close enough so that the crystals can actually form between the solvent molecules and each other. Now, mathematically, we can calculate these changes, but what I want you to notice about these calculations is that they are remarkably similar. For boiling point elevation, delta TB, now just a word about our nomenclature here. Anytime you see that Greek letter delta, that indicates that something is changing. In this particular case, what is changing is TB, the boiling temperature. Down here, we see delta TF. So we see a change in the freezing temperature. That's what TF refers to. And what we should notice is that the calculations for both are very similar. In fact, they look pretty much the same. The freezing point depression, the change in freezing point, is equal to Kf times M. M is the molality. The boiling point elevation, the change in the boiling point, is equal to Kb times the molality. Now, these values, Kb and Km, these are both constants. And these constants and they are specific to the solvent. And these are values that you can actually look up, and they're pretty easy to find. So KB, KF, these are both constant values that we can find. They are specific to the solvent itself. So water has its own KB and KF. Toluene has its own specific KB and KF. Benzene has its own KB and KF. Ammonia has its own KB and KF. They all have their own values. And you can find those values on a table like this. So this is a table of common solvents. You have water, you have benzene, ethanol, carbon tet, chloroform, and you can see that the table usually gives the normal boiling points and normal freezing points of the substance, along with their constant values, KB for boiling point, KF for freezing point. Now, what's kind of cool and interesting about these values is that you can tell a lot by the value of KB or KF in terms of the polarity of the solvent. You can see that the lower the number is for KB and KF, the more polar the solvent is, the more attracted to itself it is. And so large values of KB, KF indicate that we have a substance that's relatively nonpolar. And so we're going to see large fluctuations in the freezing point or boiling point of the substance, because we're going to get far better interactions between solute and solvent in their cases than they would by themselves. Whereas with water, water's got great hydrogen bonding. It's really stuck together very, very well. And so we don't tend to see large fluctuations in its boiling temperature or its freezing temperature. And we can see that there is a general trend here as far as that is concerned along those lines. Now, before we move on to doing some examples here, I want to pull out one other concept that is important to this discussion. But was not mentioned specifically on the slide. So, Van't Hoff factor. So the Van't Hoff factor is something that when we have a solution that is an ionic compound dissolved in usually water, the Van't Hoff factor comes into play. And what we use the Van't Hoff factor for is the molality in our problem, the molality in that equation. It isn't actually the molality necessarily per se that we would have calculated in calculations like we did yesterday. what we have to do is we have to account for total molar concentration. And where that gets complicated is in ionic solutions, total molar concentration can actually be greater than just simply finding the number of moles of the salt per kilogram of water. We can estimate total molar concentration by multiplying molality times the Van't Hoff factor. And the Van't Hoff factor can be estimated by determining the number of ions per ionic formula unit. So what I mean by that, sodium chloride. When sodium chloride dissolves in water, it becomes sodium plus and chloride minus. Which, if we do the math, means that we're going to get 2 ions per formula unit, 1 sodium ion and 1 chloride ion. And it is this 2 that we can use to estimate the Van't Hoff factor. So for ionic compounds, we do some slight modifications of our equations. Delta T B is equal to I times KB times M. And it's this I that is the Van't Hoff factor. And then M, of course, is the molality. And then for freezing point, very similar, delta TF, which would be equal to I times KF times M. And so total molar concentration we can estimate as I times molality. And so let's just do a couple of examples of this just to kind of get used to using this. And so some problems will give us the Van't Hoff factor, will tell us what it is. But if we aren't told, we can always estimate it by using this methodology with the number of ions per formula unit. So if I have magnesium oxide would give me a magnesium ion and an oxide ion. I would end up having 2 ions per formula unit. So my Van't Hoff factor would once again be 2 in this case. If I had aluminum chloride, I would have an aluminum ion, Al plus 3. I'd also have 3 chloride ions. So my Van't Hoff factor here, I'd have 4 ions per formula unit. And so my Van't Hoff factor I would estimate at 4 in that case. All right. Does anybody have any questions? Can you kind of see where I'm going with this?
I don't have any questions.
Okay. Okay, so again, this only applies when we have an ionic solute. If our solute is molecular, like sugar, like ethanol, or like any nonpolar combination of solute and solvent, we're not going to see this applied. In those cases, the Van't Hoff factor is equal to 1, and molality and total molal concentration are exactly the same. And that's actually the case here in this example. So we're told that cinnamon owes its flavor and odor to a compound called cinnamaldehyde. Cinnamaldehyde's formula is C9H8O. What we need to determine is the boiling point elevation of a solution where 100 milligrams of cinnamaldehyde is dissolved in 1 gram of carbon tetrachloride. So both of these compounds here are organic and are nonpolar. So in this particular case, our I value is equal to 1. All we need to do is we need to figure out the boiling point elevation. So we need to figure out delta TB. And delta TB is equal to I KB M. I, we know, is 1. KB, we are told, is 2.34 degrees Celsius per molal. The only thing we don't know is the molality. For the molality, we're going to have to figure out what the concentration of this stuff is. So to that end, 100 milligrams is equal to 0.1 grams of cinnamaldehyde. And we're going to need to convert that into moles. Molar mass of cinnamaldehyde, 12.01 for each carbon times 9 carbons. 1.01 for each hydrogen times 8 hydrogens. And 16 for oxygen is 132.17. And so 0.1 divided by 132.17 is going to give me 7.57 times 10 to the negative 4th moles of cinnamaldehyde. Now, molality is equal to moles per kilogram. So I've got my 7.57 times 10 to the negative 4th moles of cinnamaldehyde. And my 1 gram is 0.001 kilograms of carbon tetrachloride. So 7.57 times 10 to the negative fourth divided by 0.001, I get to three significant figures, 0.757 molar cinnamaldehyde. And so that is the last piece of the puzzle here, 0.757 molar. And so my boiling point elevation is equal to 1 times 2.34 times 0.757. I'm going to get a 1.77 degree Celsius boost in boiling point. So, important thing to note and remember here, this is not the new boiling point of the carbon tetrachloride solution. This is how much higher the boiling point is compared to pure carbon tetrachloride. If I wanted to know the boiling point, I would need to go back here and look at carbon tetrachloride and see, okay, carbon tetrachloride boils at 76.8 degrees Celsius. And so I would add that value to this. So the new boiling point would be the combination of those two together, which to one decimal place would be 78.6 degrees Celsius. So important distinctions to make there between elevation of boiling point and the actual boiling point of the solution itself. They are different from each other. And so in the case of boiling point elevation, we would add this to our existing boiling point to get our new boiling point. In the case of freezing point depression, we would subtract this value from the freezing point to get to the new freezing point. Any questions about this example?
No.
Margaret, over here. Margaret, come see Mama. Margaret, come see Mama.
All right, let's look at this example then. Calcium chloride is one of the primary components of road salt, especially municipal road salts, what they spread out on the roads in the winter months to keep them from freezing. Question is, could calcium chloride melt ice at negative 20 degrees Celsius? Couple of assumptions here. We have to assume that the solubility is 70 grams per 100 grams of water, and that the Hoff factor of the saturated solution is 2.5. Kf for water is 1.86 degrees Celsius per molar. So there are lots of ways to approach this problem. The way I would favor is to take this information here at the end and figure out what would the freezing point depression be, how cold can the water get without freezing, and then compare it. There are other approaches, but this is the one that seems to make the most sense to me. And so from that standpoint, our freezing point depression is equal to I times Kf times M. And we are told already that the Van Hoff coefficient that we need to use the Van Hoff coefficient we need to use is 2.5, 2.5, and that our Kf value is 1.86. So very similar to the last problem, what we really need to figure out is the molality. Now, in this particular circumstance, molality has been partially calculated for us because we know that we have 70 grams of calcium chloride for every 100 grams of water. Now, to turn this into a molality, all we need to do is convert this into moles and this into kilograms, both of which can be relatively easily done. So to do that, we're going to just employ some more classic dimensional analysis. And so the first thing we ought to do is molar mass of calcium chloride, 40.08 for calcium, 35.45 for each chlorine, and there are two. 110.98 grams of calcium chloride in every mole of calcium chloride. And then to do the conversion for grams to kilograms, I need 1,000 grams in every kilogram. And so if I follow this all the way through, my grams of water cancel, my grams of calcium chloride cancel. I end up with moles of calcium chloride per kilogram of water, which is molality. 70.0 times 1,000 divided by 100 divided by 110.98 to three significant figures. 6.31 molal calcium chloride is my result. So at the solubility limit, we get a pretty concentrated solution of calcium chloride. Now with that knowledge, 6.31 molal All right, 2.5 times 1.86 times 6.31. I get a freezing point depression of 29 degrees Celsius. Now remember, for freezing point depression, to find the freezing point, we have to take the normal freezing point, which is 0, and subtract our depression. And that would give us a freezing point for this solution at negative 29 degrees Celsius. So the key question here, what we started off wanting to know, can calcium chloride melt ice at negative 20 degrees Celsius? And the answer there is yes. And the way we know is based on the fact that this particular solution, if we got to the saturation limit and everything else was considered ideal, this could melt ice all the way down to negative 29 degrees, as opposed to just negative 20. So since this exceeds that, we know that this is possible. Any questions about this example?
Nope.
All right, let's do this one together, and we'll just kind of walk through it. Here we have a seawater concentration where the concentration of the sea salts in the water is equivalent to about 0.560 moles of NaCl per kilogram of water, and the Van Hoff factor is 1.85. Now, the key to this one, the trick to it, is recognizing that 0.560 moles of sodium chloride per kilogram of water that is our molality. So we've already got the molality figured out. We've already got the Van Hoff factor figured out, and Kb is a known value, 0.51. This one's actually really easy to solve. Delta T B is equal to 1.85 times 0.51 degrees Celsius per molal times 0.560 molal delta TB is therefore 1.85 times 0.51 times 0.56. I get to two significant figures, 0.53 Now, to get the boiling point, I would have to add this to the normal boiling point of water. Normal boiling point of water is 100 degrees C. And so we would expect this solution of seawater to boil at 100.53 degrees. And so, again, it's important to note that even though this is a relatively small concentration, the impact of water is that we're not going to see massive fluctuations in the temperature. Keep in mind one of our previous examples, the one with the cinnamaldehyde. We saw in that one, even though we didn't have a whole lot of high concentration there either, it was about 0.9 or whatever, the temperature went up by almost 2 degrees. Here, even though we've got the Van Hoff factor, which is helping to effectively double the impact of the boiling point elevation, it's still not that big of a deal. Half of a degree for something that's, anyone who's ever gone to the the beach or swim in any kind of body of water that's not a lake knows that the ocean's pretty darn salty. And yet, if we went and took that water and tried to boil it, it wouldn't take that much more energy to boil it versus anything else. Anything else in water. All right, any questions about this example?
Nope.
All right, so we're going to switch gears then. We're going to move off of talking about boiling point and freezing point. We're going to go to our last colligative property. Our last colligative property concerns osmosis. Now, osmosis is something that you're probably familiar with, especially if you've ever taken a biology course. You know that osmosis is the movement of water across some kind of membrane. And so we talk most, about, membranes being semipermeable, which means that certain materials can pass through them, but others can't. Now, water will always move from an area where there's a high concentration of water to a low concentration of water. And so what we'll always see is that in terms of the solute, it goes from where the solute is dilute to where the solute is concentrated, because it's ultimately trying to even them up. So if I've got, let's say that I've got right here in the middle of me, a semi-permeable membrane that's separating two solutions. Well, on this side, I've got a whole bunch of stuff. And on this side, I've got practically nothing. Well, the side with a whole bunch of stuff in it is pretty concentrated, whereas this side's pretty dilute. And so what's going to happen is the water is going to travel from this side over here to try to dilute the more concentrated side to get it to be more like the dilute side. Now, what does this look like? Well, a picture probably helps. This is what we would call in the laboratory a U-tube. These were U-tubes far before there was ever a U-tube. And the way it works is this. You've got a U-shaped piece of glass, and in the middle of that U-shaped piece of glass, we have shoved a semi-permeable membrane. And that semi-permeable membrane is small enough that the salt and extra stuff on this side, all of that extra stuff is too big to fit through the membrane. So the membrane stops the passage of solute, but the holes in the membrane are small enough that water is able to pass through them to the other side. And so on one side of this U-tube, we have seawater, which is very, very concentrated in solute, and you can see it in the molecular picture here. On this side, we have normal saline, which is roughly salty, but not too terribly salty at all. Much more dilute, as we can compare them to each other. And so what we will see is that normal osmosis would result where the normal saline attempts to dilute the seawater, and as a result, we see a migration of liquid from the saline side to the seawater side. Now, of course, the saline cannot fully dilute the seawater. It's absolutely impossible that it does. After all, the seawater is a good bit more concentrated. But what starts to happen is that gravity starts to push down on the other side of this. And eventually, the inner balance between the force of the water going through the membrane versus the force of gravity pushing down on this ultimately results in an equilibrium taking place, and it goes no further. Now, this distance that is traveled, this is what we refer to as the osmotic pressure, in terms of if I were to push down on this side to get it so that they go back to being even, the amount of force that I would have to exert would be my osmotic pressure. And so we can define osmotic pressure in this way. It's the pressure that is applied across that semipermeable membrane to stop the flow of water from one side to the other. So in addition to gravity's force pushing down, we exert an additional force to push down on that liquid and keep it from going up. We can determine and measure how much pressure that will take by this equation. Pi, the osmotic pressure, is equal to m, the molarity of the solution, multiplied by r, which is a constant, and T, the absolute Kelvin temperature. Those are the three factors that go into determining how much pressure needs to be exerted on that object. And what we will see is that, notice again, the word total comes into play here, which means that M, that our M here, is not just simply the molarity, but it's the total molar concentration, which is equal to I times the molarity. So once again, the Van Hoff factor comes in play here if we are dealing with an ionic solution. And that is an important factor, certainly. And so that Van Hoff factor does play a role, and so it's not uncommon to see the equation drawn as this, where we combine molarity, or rather we separate molarity and the Van Hoff factor to give us that total molar concentration. Now for values of R is the universal gas constant. We'll talk more about that in tomorrow's lecture and on Thursday's lecture. But the values for R really only vary by pressure unit. Atmospheres will use this value. Millimeters of mercury will use this value, 62.36. Torr, which is the same thing as millimeters of mercury, also has the same value, 62.36. So what we want our pi value to be, our pressure unit to be in terms of unit, will dictate what our value of R is ultimately. Let's look at an example. If the total concentration of solute inside of a red blood cell is 0.310 molar, what is the osmotic pressure at body temperature? Okay, so important things to know here. This is total concentration here, so we don't have to worry about any Van Hoff factor. It's already been accounted for here. And we have a 37-degree temperature, which is normal body temperature. Now, remember, this has to be converted into Kelvin before we can use it. So there's a couple of calculations that we need to do. First of all, temperature needs to be 37 plus 273. This is our Kelvin, so this is going to be 310 Kelvin. And so the other factor that we haven't considered is we aren't told what the pressure unit's going to be. Normally, our default is atmospheres, and the reason why will become apparent in a moment here. But technically, you could use any of the 3 units. So my concentration is 0.310 molar. My temperature is 310 Kelvin. And my value is 0.08206 or 0.0821. The units on that are liters times atmospheres over moles times Kelvin. So Kelvin cancels. Molarity, remember molarity is moles over liters. So my moles cancel, my liters cancel. All that's left is atmospheres. My osmotic pressure, 0.310 times 310 times 0.0821 gives me a value to 3 significant figures of 7.89 atmospheres. Now, just as a matter of context, 7.89 atmospheres, that's a little bit less than 8 times atmospheric pressure. Now, if I did this using the 62.36 number, so just stay with me for a second, 0.310 times 310 times 62.36. The number I would have gotten there, which is perfectly viable. If you had done it this way, it would have been correct, is 5,990 millimeters of mercury, or 5,990 torr. So you could have done them this way. The thing with osmotic pressure is that it doesn't take a whole lot of concentration to get a significant increase in the pressure. And what we'll talk about next here is actually we can use that to our advantage to do some things that we hadn't really thought of to do from a quantitative laboratory standpoint. But before we get to that, any questions about this?
Nope.
Okay, so one of the places where we see this in action is with your red blood cells. Your red blood cells exist in your body, and your body is a very, very controlled system in terms of solution dynamics, in terms of temperature, in terms of a lot of things. One of the reasons why, if you ever have IV fluids given to you, they give you saline instead of pure water, is because saline is actually an isotonic solution to the rest of your body systems. If they gave you pure water, what would happen is the osmosis effect would basically take over, and the extra water into your systems would start to flood into your cells. And as a result of that flooding into your cells, your blood cells would start to swell, and your other cells, for that matter, would start to swell as well. And the net result of that is, if that continues to happen, they can eventually burst and die because of the excess liquid. By contrast, if you were given a solution that was too salty, had too much dissolved in it, what would happen there? This is known as a hypertonic solution. what you would see is that water would start to rush out of your cells to try to dilute the excess solution around them, and try to go back to this isotonic state. And in the process, your cells would shrivel up and ultimately die in that state as well. And so that's why saline solutions are so specifically regulated to very specific concentrations in hospital settings, because they're designed to keep that person and keep their cells at a healthy level. Another thing we can see used as application for osmosis is in desalination. Now, in desalination processes, there are two primary ways that we can get salt out of water. And so this is really particularly applicable in countries that are islands, that do not have freshwater sources inherently inside of them. And so desalination is one of the ways that we can get drinkable water to those people. And there are two primary ways that you can do it. You can distill it. You boil the stuff to death, collect the vapor, and the resulting vapor can then be used for drinking or washing or whatever. Problem with distillation is it's very energy intensive. Requires a lot of energy to heat up the water to its boiling point, and to do that for a large enough scale of people is very, very cost intensive, very arduous to do. In addition, if you've ever tasted distilled water, you'll notice that it's missing something, and that's because most of our water sources have a minerality to them, where even if you buy bottled water, you'll note that most bottled water tells you that minerals have been added to it to make it taste fresh, and to make it taste like water, as opposed to just kind of this flat, kind of lifeless liquid. And that's the reason why. So more common processes for purifying water involve reverse osmosis. In reverse osmosis, what we do is we take that idea of osmotic pressure and we actually amplify it. So let's take that example that we saw in the last problem where we had to apply 7.89 atmospheres of pressure just to stop the flow of osmosis. Well, in a reverse osmosis scenario, instead of just applying that 7.89 to stop it, we would actually apply greater pressures than that to force the water to go from the contaminated solution into the purified solution on the other side. And so this is one way that it often works. And so you put water into these systems, the pressure pushes that water into these semipermeable membranes. The membranes keep the salt crystals out. The purified water ends up into the collector, and then they can do this however many times they want to get a purified water product for drinking or for whatever purposes. The last primary application that we use osmotic pressure for a lot is for determining molar masses of substances. Now, as I said before, it doesn't take a very high concentration of substance to get an appreciable amount of pressure. We saw in the last example, a 0.31 molar solution generated a pressure of nearly 8 atmospheres. So to that end, if I take a really low concentration solution of something and it gives me a value that I can measure, I can use that to try to figure out some stuff that I don't know. So if I have an unknown sample of something, I can use small amounts of that, dissolve them in small amounts of water or carbon tetrachloride or Pick your favorite solvent depending upon the circumstance. Make a dilute solution of it, measure its osmotic pressure, and then compare that sample, do some back calculating to figure out what its molar mass is. And I can use that to kind of figure out what the substance is and characterize it, get some ideas of what its makeup is and so on. So let's take a look at this at an example like that. In this example, I have a 47 milligram sample of a water-soluble non-electrolyte, and it's dissolved in enough water to make 2.5 milliliters of solution. So again, look at this. Small sample, small amount of solution. And yet, the osmotic pressure we measure is 0.489 atmospheres. So that small amount of solution generated nearly half of an atmosphere of pressure. The question is, what is the molar mass of the compound? Now, to solve this, we have to take into consideration, again, our definitions. Molar mass is going to be equal to grams of sample divided by moles of sample. So I've got 47 milligrams. So I've got a mass of the sample. I'll just need to turn it into grams here in a minute. I need to figure out the number of moles of the sample. Now, the only way that I can do that is by using this osmotic pressure. And the way that I can do that is understanding, okay, osmotic pressure is equal to molarity times R times T. Well, I've got my T. R is dictated by this value here, and I've got my value of pi. I can solve for molarity. So 0.489 atmospheres is equal to molarity, which I do not know, multiplied by 0.0821 liter atmospheres per mole Kelvin. And then multiplied again by 25 degrees Celsius, which converted to Kelvin would be 298 Kelvin. So if I do out my algebra, my molarity is going to be equal to 0.489 divided by 0.0821 divided by 298. My molarity to three significant figures is 0.0200 moles per liter. I can use this to find my number of moles. So 2.5 milliliters is 0.00250 liters. And what I get is 5.00 times 10 to the negative fifth moles of this substance. So now molar mass is equal to my mass, 0.047 grams, divided by my moles, 5 times 10 to the negative fifth. And to two significant figures, I get 940 grams per mole. So where we see this the most often right, so where we see this the most often is in these kinds of compounds where we're characterizing something that is molecular, something that is biological, something that is complex, like a protein or a complex carbohydrate, something that has a lot of complexity to it. And we're using that and this methodology to help find its molecular weight, because the molecular weight is usually quite substantial, and something that other kinds of techniques like mass spectroscopy might not be able to do, because the heat of mass spectroscopy might cause the protein or whatever to denature or break down well before it ever gets to the detector. All right, any questions about this example?
No.
All right, one more example, and then a brief discussion. And actually, we'll save the discussion of Henry's Law for tomorrow. There are no homework or quiz questions about it, but it'll actually move us very nicely into talking about gases. So, last question here. We have an aqueous solution we make by dissolving 11.9 milligrams of a non-electrolytic protein in enough water to make 4.88 mils of solution. The osmotic pressure is 523 millimeters of mercury. What is the molar mass? So very, very similar kind of technique here to what we did in the previous problem. We have an osmotic pressure, 523 millimeters of mercury. We don't know the molarity. We aren't told the temperature, but we can assume it's 25 degrees Celsius, which would be 298 Kelvin. And since we're in millimeters of mercury, we're going to use 62.36. Liters times millimeters of mercury divided by moles times Kelvin. If we do out our algebra, 523 divided by 298 divided by 62.36 would give us a molarity of 0.0281 moles of our protein per liter. And so we could do the same kind of thing again. One little trick we could do is we've talked about the idea that molar mass is equal to grams per mole. Well, it can also be equal to milligrams per millimole as well. And we're actually going to take advantage of that right here. How do I get millimoles? Well, if I multiply by the milliliters here, 0.0821 times 4.88 milliliters, I would get 0.137 millimoles of protein. And so if I wanted to save myself a little bit of calculation work here, where I had to turn this milliliters into liters and then turn this milligrams into grams, I could use this methodology to do that. Molar mass is equal to 11.9 milligrams divided by 0.137 millimoles. And so to three significant figures, 11.9 divided by 0.137, I get 86.9 grams per mole, or milligrams per millimole, however you want to look at it. Now, if we just want to prove to ourselves that this actually works that way, we can kind of follow it through. And what we'll notice is that we end up dividing this number by 1,000 and that number by 1,000. And that's why, you know, the two divisions by 1,000 basically cancel each other out. But if we just wanted to prove that to ourselves here, .0281 times 0.00488 would give me a 1.37 times 10 to the negative fourth moles of protein. Um, 11.9 divided by 1,000 is 0.0119 grams divided by 1.37 times 10 to the negative fourth moles. And again, if you do that, 0.0119 divided by 1.37 times 10 to the negative fourth, you get the same 86.9 grams per mole. So like I said, this is just a little bit of a mathematical trick. When it comes to molar masses, and this would work in a number of different ways. If I had kilograms and kilomoles, I could do it that way as well. If I had micrograms and micromoles, I could do it that way as well. Regardless of how you do it, if the base unit in the numerator and the denominator is the same, it works all the way up in this case. And so 86.9 grams per mole would be the molar mass, which for a protein is actually really, really, really small. Most proteins have molar masses in the thousands of grams per moles, not in this small range. Right. Any questions about molar masses using osmotic pressure?
No.